Welcome to MakeCast. I'm Dale Dougherty. As we begin to congregate in classrooms and offices and bars and restaurants, how do we know we're safe? We're going to be looking at building and deploying CO2 sensor devices that can measure the accumulation of CO2 in a confined space. As you'll learn, it can be a pretty good indicator on how effective the ventilation is in that space. My guest today is Guido Berger from Germany, who's written about this, wrote an article for Germany Make edition called the CO2 traffic light. Part of this is giving feedback to people in that room what the level of CO2 is. We're going to be talking about how you measure this, why you measure this, and how you might display it, how you might deploy it. Welcome, Guido. So good to see you.
And I'm glad being with you. I'm honored being on the call today.
So give us a little background on yourself.
I'm a maker, I'm a sailor, and an engineer. So these are three things in one box, which makes the sailors, the curiosity is exploring new lands, being out in the wild, and being with a team on a ship, on a boat, and make that from one harbor to the next harbor while we have fun and explore the world. The engineer and the maker are in constant battle. The engineer wants to do it super right, the German precision and engineering, high quality, and think 3 times to do it right. And the maker is just, ignore the specification, just do it, just get it done now. So this is probably how it describes me best: a constant battle around innovation, doing it quick, fast, but as well right.
You are a developer of the Octopus board. We're going to be looking at some devices that you built, that you've actually deployed in classrooms, and can show us some of the results that you might see. Can we get lots of people building these devices, particularly those people are students, deploying them in their classroom, analyzing the data, and actually just the readings themselves are telling them how to take actions like open a window or reduce the number of people in the room or move somewhere else. This is a simple, but I think a really amazing kind of project in education, but it's not by any means limited to education. So do you want to show your presentation?
Yeah, let me jump to that and give a bit introduction why we are doing this, how we are doing this, and hopefully you can see the screen now. That's me working in a classroom. So we started 2016. We is a professor from the university here in Germany, and we both had the idea we need to get the pupils and the students in the schools early access to all the technology foundation that we need in this digital age. So how they can work with sensors and the Internet of the Things, how they can bring their ideas and innovations to life in an early age already. So we're working with pupils in the age of 14, 15, even 11. And you see myself here in a workspace, in a makerspace, actually crafting these CO2 traffic monitors with the kids. Let me advance the slides and go in a bit of the theory and the background why we are looking at CO2 and why that is important in the pandemic. So on this screen, you see one of the main paths for the virus is the droplets or the aerosols. So why we are speaking, we are exposing and pushing a lot of humidity out of the body, which is concentrated in these droplets. The droplets are the larger pieces. You see the dark red dots. They are falling pretty much down to the ground or to the table or to the screen in front of you when you're working and talking to your screen, like here in this presentation. And there are other droplets, which we call the aerosols. And the aerosols are the smaller parts. And we see them in a second in action. So anyway, these droplets and aerosols are the carrier for the virus. It's one way how the virus can be transmitted. So this is why we got asked to wear masks as people that might be infected or people that want to be protected against the virus. So the masks is helping that we are not inhalating these aerosols, which could potentially carry a virus. If we are in a classroom, this is an animation of a typical classroom environment. We have the students, the kids, the pupils sitting, there's the teacher, the desks, and so on. And here we're looking at the aerosols, which are in a size of 5 micrometers. And on the mid-side screen, there's a student, and we're looking at him, and he's breathing. He's breathing normally, quite normally, but he's emitting these aerosols and droplets. Now we forgot about the droplets because they are falling quite quickly down to the table or to the floor. But the aerosols, the little ones, the 5 micrometers and smaller ones, they are still in the air and they're traveling in the air. They're staying for hours in the air and they could carry a virus. Now, if you look into this animation, it's like a 2 minutes thing from the left to the right. We're looking for 2 minutes, what is happening with the distribution of these aerosols in the room. And on the right side, the aerosols are really nicely distributed in all the area of the classrooms. They like to travel, they like to stay, and they like to distribute equally in the room. Now, they're in a size of a very small thing, 5 micrometers. It's nothing that you can see actually, and it's hard to detect. So what we are doing here is we are taking a marker that we can easily measure, and that's CO2. So we are emitting CO2 while we are breathing every time. That's the only source in a classroom for CO2 typically. It's the human beings. While they're talking, speaking, doing their studies, we produce a specific amount of CO2, and the CO2 level rises with the activity. So if we are speaking loud or if we are singing, we are emitting more CO2. At the same time, we are emitting more aerosols as well. So the CO2 becomes a marker for the aerosols being in the air. Now, let's see what is happening here. This is a curve where we are looking at the CO2 as a marker for the aerosols, which could potentially carry a virus. We are not seeing the virus. We are not detecting the virus. We're making a connection to a potential source for the virus.
And that's really clear, where this is not detecting coronavirus. It is looking at the conditions on which it may be passed on.
Exactly. So here you see a typical picture where we see a curve from 500 to 1000 ppm of CO2, parts per million CO2 in the air. So that means we have 1 million parts of air and 500 of them are CO2. So this is pretty cool how we can measure this. I'm coming to that, how we measure it. But this is a typical curve that we see. We are in the room. The curve starts around 400 something ppm, and then it is going smoothly up to a level that reaches 1000. 1000 is one of the first marker that we have for a threshold. So 1000 ppm CO2 in a room means we should start opening the window, getting some fresh air in. And that's what we are doing here. We are opening the window and quickly this value, the CO2 marker for the aerosol, is falling down to something around 420. 415 ppm CO2 is really the value in outdoor conditions. So fresh air outdoors has this 415 ppm of CO2. Now, there are 2 steps of the curve here. This one is going quickly down, and this one is going slowly down. What's the difference? The difference is here, we are opening the door and the window at the same time. So we allow a quick exchange of air. We're allowing to get the wind blowing into the room and moving the aerosols and the CO2 quickly out of the room. This one on the right-hand side is just opening a window, maybe just partly. That's what we do typically to ventilate our rooms. We are not wanting to sit in a wind, maybe a cold wind blowing through the room. We just open the window a little bit and we have a feeling that there's fresh air coming in it. But in truth, there is not much happening. See, this could be an hour, literally an hour to get fresh air conditions in the room when we look at CO2.
What are those 2 German words?
Querluft means that you have door and the window open and the wind is blowing through and you're sitting in the wind literally. And Kipplüften means that you have the window just opened a little bit.
Okay.
So coming to learn how we ventilate the room best. If you have an air condition, probably you will see something between these two curves. It depends how much air you get in the room through the air condition. And with that, how much fresh air you get into the room. If you have a ventilation system, an air condition that's just cycling around the air in the room and is not bringing fresh air in it, well, the CO2 will still stay there for a while, and the aerosols as well. So we need to have a level of fresh air coming in the room to really get to this point where we see a sharp drop in the reduction of the CO2. And that's exactly what we want to have. We want to have a sharp drop in the CO2 level. And we will see later in the plots that we are seeing why this is so important. How we measure this. This is a little bit, not really rocket science, but it's technology that is really helping us to do so. Here you see a sensor, that's the Sensirion SC30. There are other sensors out there which are called NDIR. We are looking at CO2 in a way that we expose here in a light source infrared light. And we have a tube which has actually two channels. And the CO2 is getting through these holes into these tubes. So when there's CO2 present, it finds its way into the sensor. And by the way, CO2 wants to be distributed equally in the room. So we don't need a ventilator or something to get the CO2 into the sensor. It's traveling automatically into. And so if the CO2 gets into this tube, into the sensor, and we have the infrared light emitted here, it's a special source with a special wavelength. And that infrared light is absorbed by the CO2 molecules being in the tube. So the more CO2 we have in the tube, the less infrared light we see on the detectors here on the left side. So the CO2 is absorbing the infrared. And with that, we see less CO2 here at the detectors. So the more CO2 is in there in the tube, the less value we have here on the detector.
So this is an optical sensor?
This is an optical sensor. We talked about the optical sensor, but there are other sensors as well, which are non-optical. And so you might see sensors for $50 or sensors for $10. What is the difference? And here's a plot that shows the difference. The top curve, the orange one, is the optical sensor, what we call the NDIR sensor, which is looking after the infrared absorption of the CO2 or by the CO2 molecules. And it works really nicely. So you see here me sitting in my office. I'm having a talk starting at noontime, and I'm talking and CO2 level is rising. I get at 1000 ppm a warning. I'm opening the window. The value is dropping down. Not really to the 400 that we want to see, but close to. I'm closing the window and it goes up and down and up and down. So this is what we measure with the CO2. And the other sensor, which is a non-optical sensor, which is a MEMS sensor, is looking at VOC, at the organic substance like alcohol or also from the breathing. This is what we measure with the other sensor. And this
is a VOC sensor? VOC stands for volatile organic compounds.
Yeah. The VOC sensor is also capable with some mathematics to calculate an equivalent CO2. So if you see a small e in front of the sensor specification talking about CO2, then this means equivalent CO2. This is a calculated CO2 value. And here you see a comparison of both. You see when this CO2, this optical one, is detecting a growth, we see this one is detecting a growth as well, but then it becomes a static value. It's not anymore growing. If we open the window, we see the value is dropping down, and you see there's a relation between the two, but they're really measuring something else. So if you looked at as a one day in my life, there's a night here in front. The CO2 sensor is nothing detecting during the night. And it looks like that my day starts really at the noon time because there's some action and the values are changing. But if you look at the VOC sensor, we are seeing in the night, there's a lot of things happening as well, which is not seen by the CO2 sensor. And you see there's some curves up and down. And here, this is literally what our human body is doing at night. We have some breathing going on. We might digest our good dinner from the evening and other things going on in the body that we can sense actually here. And we see at 8 o'clock, there's already some action happening. So probably I waked up at 8 o'clock and maybe I went to the bathroom here and so on. So you see, we are looking at something totally different. So when we want to monitor the CO2 emitted by a human body, we really need to have this optical CO2 sensor. But if we want to see more, then we want to have a VOC sensor. And what is the reality in schools is if we have the kids using hand sanitizer or disinfectants or alcohol to wipe and clean the desks, the CO2 sensor will not see that because it's just looking for CO2 molecules. The VOC will detect that clearly, like a spike like this. So this could be like a hand sanitizer being used in a room. And well, we want to have a ventilation as well. We want to have an alarm there showing us, oh, there's some chemicals in the air. Let's get open the windows. Now, another element that's important as we are talking here about a traffic light, a warning system. Typically, the CO2 monitors that are available as a product, they have a red, yellow, and green light system. So green light means everything is okay. Yellow means you should open the window, and red light is the ultimate warning. And the master red light is 2000 ppm, the yellow light is 1000 ppm, and below 1000 ppm, we're talking about a green light situation. We looked at some curves before and we saw the dynamic there. This is not represented by the traffic light. And that's why we said we need to have a visualization like here with this matrix display where we see the curve going. So how is this curve evolving over the time? How quickly we get the air exchange, how quickly we get fresh air in it. Because it's a very static system, what we see. If you have seen the curve before, there was 1 hour, if we haven't opened the door and the window at the same time, that we have, well, it was 1 hour to get from 1000 ppm down to 500. That's pretty long. So we want to see that. We want to see the curve and the movement of the curve behind the scenes. So here you see another representation of what we are doing with the kids. We have a bunch of girls there, and that's very interesting. So probably one of my highest attendee number in girls was building the CO2 monitors. And we use different displays. We give the students and pupils really their creativity, how they want to present the values, how they want to have this warning, how they want to have a visual representation of what we are seeing. And we came to a tool that we look into later. This is the kit that the pupils are now building these days. And it's easy to build. It has tons of options and it gives us the flexibility. How we are coding it, we will see also in a second. We are using these graphical blocks called Ardublocks, or you might know Blockly or Scratch. It's the same way how we stick these code blocks together. We don't need to be super experts in coding. We just need to know, oh yeah, this is an algorithm. We are looking for a threshold. We are going to set the light red, yellow, and green, and we're almost done. And now, before we build one of those sensors here live on stage, I want to show you the results, what we are really seeing in the classrooms. Now, this is a view on one of the monitoring systems. We are using here open source Grafana and MQTT and a ton of technology to make that a real-time experience. But that is not so important. It's more important to see the results and the data plots that are exposed here. First of all, you will notice we not have only one traffic light, we have 5 traffic lights. Why this? CO2 is the marker for the aerosols. That is really important. That gives us the indication when we open the window and when we can close the window. but we don't want to freeze in a cold season time like in early spring or winter. So we want to monitor maybe the temperature as well. Humidity is a very important indicator. Humidity should be between 40 to 60%, but in reality, we are down to 20 or 30%. And this dry air is a good condition for the aerosol to stay even longer in the air. So we want to monitor humidity. We should have it above 40%, hard to get typically, but we should have an eye on that. Then we are monitoring the VOC, which is calculated into a thing called the Indoor Air Quality Index. That's another parameter that we can look in. And we talked about that when we use hand sanitizers or alcohol wipes or anything that is chemical in classroom, we want to use that and see that as well. By the way, if we go into a restaurant situation or into a club or into any other situation outside of school, this parameter could be really interesting to monitor at. As well, the next, which is the PAX counter, we are counting people. We are having a Wi-Fi module on our sensor, which gives us for free another channel to look at, which is the number of mobile phones in the room. So when we have a relation between human beings carrying their smartphone with them, and most of us are carrying a smartphone, and if the smartphone is on and is looking for a mobile hotspot or for a wireless hotspot, we can detect that. We can count it actually. And you see then how many people we have actually in the room. Because having more people in the room is probably a higher risk than having just a few people in a large room. So we want to look at that as well. Now, a bit of theory about the sensors. These sensors, whatever type of sensor we are using, they have typically accuracy, which is plus minus 30 or plus minus 50 ppm. So whenever they are telling us this is 781 ppm, there's a plus minus to it. And you see it here. This is a comparison of a couple of different sensors in the same room situation. And you see there is like a bandwidth between the two sensors. And that bandwidth could cause a bit of trouble if we have a threshold for 1000. Maybe we want to start early with 800 or 900 to get a warning and not wait for 1000, because like this sensor is crossing the 1000 threshold and at 0, and the others are crossing the threshold 3 hours later. This is a big difference. So we need to learn a bit about our sensors and how the sensors are working, what the threshold is. This is shown here in this graph. The other thing we need to look at is how accurate is our sensor? Is that sensor calibrated? And that's what we are seeing here. We are looking here at, and that's for the rest of the slides that I'm showing here, the same. We are looking at 7 classrooms represented by these colors, and we are looking at the CO2 level that we are measuring. And what we are seeing on a Sunday where nobody is in the room and in the classrooms at the school, we see all these sensors are showing roughly the same value in this threshold, in this tolerance bandwidth, which is given by the sensor, around 400. So we are actually seeing fresh air on a Sunday in the classrooms. That's great, because then we know the sensor is working, the sensor is calibrated. Now you see this blue curve here is another room. This is a bit off. This is showing us a value between 200 and 300. This means this sensor is not calibrated. So we need to calibrate that sensor to make it sure that it shows the right value and not is 200 ppm. This would be bad for an alarm system. Now, how can we calibrate the sensors? We talked about that the outdoor air is having something like 415, 420 ppm CO2. And this is wherever you are on the globe, the same. There's only a little bit shift if you're going altitude higher or lower. So if you're on a mountain, you have a different CO2 level outside. But typically we are here on ground in Earth, and there's typically the 420 something values. Now, as we know that, we can bring this guy, this blue sensor, out into the fresh air and press our calibration button. And that makes them telling the sensor, what I'm seeing here is 415 ppm. So this curve will move after calibration into this crowd and be relevant for us for measurement. Now, a little bit looking into the details and how we can improve our ventilation and our quality in the classrooms. This is a 1 week in one school. And we see the Monday, Tuesday, Wednesday, Thursday, and Friday. Saturday and Sunday is off. So you see the values of CO2 are declining slowly. But as we have seen on the weekend, we are around the 400. We have this blue one being an exception. Now let's zoom a bit into. Here we see the Monday. And these are 7 classrooms and the CO2 level that we are measuring.
Right. And to be clear, these are identical devices. Basically.
Identical sensors, same calibration. Actually, they're on the same floor level, but different classrooms, different teachers, different, roughly the same number of kids. In the classrooms, we have typically 30 kids per classroom, which is important because you will see in a second what is happening when we have a lot of people in the room. Now, if you just look at this, and I'm not saying anything to this, looks really confusing, right? This is a lot up and down. There's no real control seeing here, that there's a smooth up and down. Like if that would be an air condition, the air condition would be probably broken soon because it's going to switch it on and off, on and off, on and off. There's not really a control and a pattern seen here. This is like a zoom in. So I'm picking out now 2-3 classrooms from that crowd to look a bit into the details. Now, the class starts here at 7:30. So the kids are moving in and you see how quickly we are going from a fresh air condition to an alarm situation. That's literally happening in, let's say 20 minutes. We have the first alarm.
What's the peak at? What's the value?
That's 1,100 ppm.
Okay.
But now think this room is equipped with a CO2 traffic alarm system. So the teacher gets an alarm signal, a yellow, when we're over 1,000. If you don't have this system in place, imagine what happened with this curve just traveling up and up and up. So you could hit easily in this 1 hour. In Germany, the classrooms are like 45 minutes, and then there's a break of 5 minutes or 10 minutes. But if you would say this curve is going with this up and up, we are hitting the 2,000 and 3,000 ppm easily. And this is due to the number of people in the room and what the people are doing in the room. Now, the teacher got the warning here, and a couple of minutes later, he opened the window, and we see how quickly, and the door, by the way, how quickly this value is dropping down. It's hitting 500 something. And then he's closing the window, and you see it's going back up again. Now, it looks like there's a break coming up here because there's not much more happening here. And actually, this is a longer break in the school, which is happening here. So the curve is staying static and is not more happening in the classroom. Let's see another curve. Same room situation, a different room, same floor, same system. Our kids are coming in, the value is traveling up, the teacher is getting an alarm here, a yellow warning. He's opening the window. Wow, that's great. The value is traveling down, but it's not going too much down. It's 750 something. Closing the window, and you see how quickly this value is catching up again and is traveling above 1,100, close to 1,200. Again, he gets a warning, and it's opening again the window. Not long enough, closing the window. And again, you see how quickly the value is going up. And what you're noticing, every time we are growing and growing the aerosol density as well as CO2 level in the classroom. We are not really efficiently ventilating the room. Even he opened the window twice. Again, he is coming the longer break in the school, the morning break for breakfast and so on. And the window and the doors are open. The pupils are leaving the room. You see how quickly the value is going down, and even fresh air is now in the room. We are hitting the 250 value. This is really cool. But we have seen this was not an efficient ventilation. What's our recommendation? We need to have a little longer open the windows, maybe not just 5 minutes, maybe 10 minutes, to really make an efficient ventilation situation. And that's what the inside of the data plots is showing us. Another situation, again, you see the up and downs. This is not what we want to see. We want to see clear drop of the value to fresh air. We want to have a stay there for 5 to 10 minutes and then see how the situation is, and maybe even keep the window open for more time, depending what is happening in the classroom. So this is what we get out of the system. We get a clear warning indicator. We need to see the curve and how the curve is over the time. That's why we need to plot. And that's why we need to have this system being connected to the Wi-Fi system. So we can use it on the tablet, on the mobile phone, and maybe on a server to store it and record the data. So it was easy for us to get access to the schools mid of last year and do the first trials. And over the time, we found what is going on there, what is happening, how we are building things, how the kids can build the tools themselves, how important it is to educate about what is going on in the air. Can we visualize what is going on in the air? We can't see the virus. We can't see the aerosols. But now with the CO2 as a marker, we can make these plots that you have seen. And now we can give guidance to the teachers and the class how they can be more efficient in ventilating their space, and with that reduce the risk of an infection.
I like that idea of CO2 as a marker for certain conditions. So let's look at the build. Let's go through that here.
Let's do so. Let me switch to my table camera first to give you an introduction to the hardware, to the actual kit. So what we are seeing here is a kit in action. I was talking already a while, so my CO2 level raised here in my room already to a red light situation. It's a good time to open the window, and we will see later on how that works. So I'm just opening the window, and we might see that this red is going over the time to hopefully a green or at least a yellow. So what we are seeing, quickly explained on this board here, is, of course, the three lights. We have the traffic light, the red, the yellow, and the green. These are standard LEDs, like off-the-shelf LEDs, nothing specific. We can easily solder that onto this PCB board. You see already, we're getting to a yellow. The ventilation works. And this one, as I'm speaking now to the sensor, it detects my breathing CO2 level, which is, by the way, something like 30,000. So you see it goes flip forth and back because I'm breathing onto the sensor. This is the sensor. You see this yellow light here is indicating the infrared light sensor. And you see the two tubes and these openings for the CO2 to travel into the sensor. So this is our CO2 sensor, the optical sensor that we talked earlier about. And then you see here standard ESP8266 Wi-Fi, which has this full support of Arduino. So we are going to use Arduino to code this whole kit. Now, if you look at that, it's pretty simple. It's a PCB board that gives us a ton of options. So we can have the sensor that we just talked about, but we can also have a different version, a cheaper version of that. That's the MHZ19Z. That's a Chinese CO2 sensor. It's half the price of the SC30. Or we can even go to another sensor, which is the SenseAir S8. You can just plug in what you find. Why we did this? Because in the middle of the pandemic in November, we were seeing really disruption of the supply chain. So all the sensors were, as we were building all these projects, they were gone. There were no stock anymore available. So we decided to have a couple options here in the design. One reason is cost, and the other one is what is available on the market to build this project. So we have 3 options for the sensors. We have again 3 options for the compute module. So you can go with a VMOS D1, or you can go with a Node MCU, all carrying the 8266 ESP, or you can even go, let's see if I have one with a Feather 82. So all hardware modules are going into that. And then you just need to have a couple of extensions. If you want to extend that further, you can have your growth connectors up there. The LEDs are going here. You have a header for the sensor. And then you have a couple of resistors giving us the right voltage levels for the LEDs. That's it.
You told me, Guido, is that the sensors started to run out, and they were surprised that people were building these kind of devices.
Absolutely. Absolutely. As we launched this as an open document kit, we allowed the people to copy it, of course, and we wanted to copy them and give them the space to say, I want to have a different version of it, a different footprint. We wanted to inspire just by, you can build it like this, like a blueprint. And so we drove a lot of those designs just as they copied this design, but then other people starting to build their own designs. So the community spun on hundreds of projects the same way, and all were literally going with the SCD30. So now you can imagine they were built typically only for HVACs, so air conditioned systems. But if a community starts to asking for those sensors, a manufacturer can quickly run out of stock. But this is fixed now. So all the sensors that we are using here are widely available. And those sensors are available. Now, there's another version of it. And you mentioned already the Octopus before. And you see a similarity between this board and this black one is the Octopus. It has this little octopus on the back. This board we designed for the pupils or work with the pupils at school. So we wanted to have a system that's not just a new hardware. We wanted to use as many as systems in the market. So it says the Feather system, it has the 8266, it has the growth connectors, it has NeoPixel already, RGB LEDs on it, and it has a VOC sensor, the BME 680 already on. So it's pretty easy to start with that. No cabling, nothing. And we have
no soldering.
No soldering. And we have a wing design, or I built a wing design where you can have even the sensor hooked up to. So you just snap it in here and you're done. So there's no soldering. Here's a bit of soldering. No hard soldering, no SMD. It's all through-hole soldering, pretty easy. But if people are a bit afraid of soldering, you can find this growth sensor, which is carrying also the SCD30. And you can connect it to your favorite growth system, whatever that is. In my case, I'm using the 8266. And then you can connect it. And as you see, we have this Feather connector. You can have different displays connected to it, an OLED, a matrix display to show the curve. Or maybe you want to have a big NeoPixel alarm system that is much brighter than these 2 LEDs. Or maybe you want to connect a thing like this here, which is a voice recorder. And this voice recorder is simple to use. You press the button, you say, oh, please open the window. And when we see a yellow, we can use that to give us a voice alert and say, please open the window. So there's a ton of options, and probably the community knows already what they want to do in addition to it. Now, you see, by the way, there's a little switch here that we use later for the calibration. We built like a little virus display. So you see the virus here, and it's backlight by the LED. So this gives a nice visual effect. But we want to inspire the pupils really to build their own visualization. And we have a ton of creative solutions, how they build it, like a bottle filled up with sand and then put the thing on top of that. Let the creativity play how we want to have this visualization. Also, you can use, of course, if then that and home automation connection. So you can really go crazy with all that here.
Give me some ideas of price ranges for some of the different configurations you showed.
This is in a range of I give you maybe these two versions here. That's a good one. This one, the compute module is around $5 typically. And the parts here is like $1. The PCB board is $2, something like that. So we are around $10 for the basics. And then it depends what type of sensor you're going to use. This one is the probably heaviest part from the bill of material. It's around $50, depending on the quantity. The one piece quantity price is 25. So it's half the price of that. But reality is you get half the quality. Here you have two tubes, which gives you a long time stability of the sensor and high accuracy of the reading. And this one, you probably need to adjust more often. There are algorithms, which is called auto calibration, that helps to make that similar quality like this one, but there is a difference. So let's say $40 and this is like $80. But now this is the hardware. We have seen before that we're using these graphical blocks to build the program for this little guy. And let's jump to that. And we are going to look into the Arduino environment. Now, as said, we are not here to be the best coder on planet Earth. We want to build a solution that helps and understand and show what is behind these aerosols and what is going on in our classrooms. So we don't want to waste too much time doing C coding. So we use an extension to Arduino, which is called Ardublocks. It's using like the Scratch libraries for these blocks that you can stack together. And when I start that, you see it's immediately going to this visual representation. Scratch users might notice this library here. There's controls, logics, maths, variables, and for all that are blocks there. And now here's the extension of what we built over the time for the kids at the school since 2016 already. We have a block for a Wi-Fi connection. We can turn our little thing into an access point. So if there's no network available, no Wi-Fi, we make our sensor access point for your mobile phone or for the tablet or for your laptop. We support professional IoT protocols like MQTT or LoRaWAN, or we support the Blinky app, which is a nice graphical app on the mobile phone. Or we have even support for the Edge Impulse Cloud, or we have little blocks, which gives us AI capabilities on the block, on the unit itself. Furthermore, we support all the tricky things like a deep sleep. So if you want to run that on a battery, you want to implement a deep sleep, or you maybe want to have some variables stored that are even there when you unplug the unit. So maybe you want to have a threshold secured somewhere in the memory. We can write to the real-time clock memory of the ESP. So we have some tricky stuff there, which is like for the professionals. We're not going to use that, no worry. And we have a ton of extensions here, displays, RFID, particle matter sensors, a ton of things that we can use to advance this traffic light. But let's build a simple traffic light so we can see how easy that is. First of all, we need a variable memory store for our sensor reading. So I'm going to use this one and say this variable is called the CO2 level. Now I need to get the reading from a sensor, and we have a special folder here for COVID-19, and you see here are the different sensors, the golden one that we have seen, the MHZ19, as well as the SC30. And there are always two blocks. One is the sensor reading, and the other one is the one that we need for the calibration of the sensor. We are going to use the first one here, which is the sensor reading. We want to read the sensor value. And now we can see it snaps in here, like you see this triangulation goes in there. And when you hear the sound, it just snaps in, and we know this fits together. You can't put this thing here. It doesn't do anything. There's no connection. Here's a connection, and we have connected it now to the variable. Here we can select different values that the sensor is giving us. It's the CO2, temperature, and humidity, but we are going to use the CO2 level here only. Now, the next thing, we need to have a sort of an algorithm that shows us if the value is greater than the first threshold, we want to have the yellow light. It's below, we want to have the green light. And if it's above 2000, we want to have the red light. So that's why we need an if then else. And we need now a logic operator. This is a lower, and we just can copy here this value, click on the block, and then we can clone it. So I'm using the variable CO2, put it in here, and now I can make a comparison. So if the CO2 reading, the current CO2 reading, lower than a value, now I need a value, there's one here, which is 1000, then I want to have a green light. Now I have a couple options here to do the green light. One is I can use the LEDs that we have seen on the hardware board, or I can use a NeoPixel. This is like a more, advanced capability. We are supporting both. So I'm using, first of all, the LEDs on the board. Therefore, I need a digital I/O. I need to know the pin number. This is when I have at the top of my mind, the 14 for the green light, and I need to switch it on. So if the CO2 reading is below 1000, switch the green light on. Now, I'm just copying this structure again and put it in here in the else structure. Now I'm saying the CO2 should be below 2000 for the yellow light. The yellow light is, the yellow LED is on pin 13. So I need to enter here 13. And if we are between 1000 and 2000, we get the yellow light on. And now the else is, of course, the value is greater than 2000. That means we are switching on the red light, which is pin 12. Now, one thing which is missing is a delay. We want to have a sampling time assigned to this procedure, which is maybe 5 seconds. So we want to monitor every 5 seconds, what is the current CO2 value, store it in the variable, and do the comparison and switch the lights on and off. That's in a nutshell our CO2 traffic light. Very simple, very easy, straightforward. Now folks might say he's switching on the LEDs, but he's never switching off the LEDs. Well, that's true. We need to add a little more code here, which is making sure that only one light is on and not all the lights are going on over the time. I'm not going to do this here because this is just copying code and probably this is a bit boring. I'm just doing it once for the first one so you can see what I'm talking about. So I'm just copying this. And while we said 14 is the green light, we want to set in this situation 12 and 13 to low. So making sure that only one light at a time is on. Green light is on, yellow is off, red is off. And now we need to replicate that for the other situations. Maybe I do that quickly so we have a clear, good working code. Give me just a second to do that. And you see now it gets a little bit more complex, but not too much.
All you're doing is resetting the LED each one.
Exactly.
Right?
So we have now a clean operation. And we will probably want to have this in the beginning as well, where we say when we start a traffic light, we want to make sure that in the beginning of the code, all the lights are set to be off. Now you see the structure gets a little more complex, but it's still very simple. Reading the value and do the comparison and switching the light on and off. Should we give it a run?
Yeah.
Let's see. We need to do an upload to the Octopus board. This is just the hardware we call always the Octopus. If it's the soldered version, if it's the version with the SMDs on. This button just means one thing, the graphical blocks are now turned into C code in the Arduino IDE. So you now see this is exactly what we have built with the blocks. We are not using the Wi-Fi. We are switching off. We are initializing the pins. We are switching off the LEDs. We get all the things done that we need to have the CO2 sensor running. We even get a wire set clock stretch thing in there, which we need to get for a clear operation of the sensor. But we don't need to care about that. We're just getting our algorithm built here. And then you see we are reading the CO2 value from the sensor. And then we do the comparison, CO2 smaller 1000, CO2 greater 2000, smaller than 2000, lower than 2000. And if it's above 2000, we are switching the other light combination on. It's very simple. And we have a 5-second wait till we repeat the whole thing. Now, this takes a while here, always on my computer when we have a Zoom session running. My Arduino, for whatever reason, is going slow. You see it's now compiling the code, and it's then pushing the code onto the hardware, which is connected via a USB plug to the computer. So one thing that people who want to build this need to make sure is that the Arduino IDE, and we provide a download version for a packaged so-called portable Arduino IDE that you don't need to install. You just need to copy on a memory stick or on your computer. It works on a Mac, like you see here. It works on a Windows system, even it works on a Raspberry. We have all the libraries that we need already baked into this portable Arduino version. Also, we have the board manager used to provide the ESP8266 with all the settings that we need. But one thing that you need to check out is the port mapping. You need to make sure that the port is mapped to your USB cable. That's the only thing where you need to check if this marker is done, and then the code is delivered. You see it under here to this device, which is our hardware kit. Now, while this compilation is going on, I want to show you one thing more, and this is basically you have then an advanced version of the CO2 system. I'm going to kill a bit of the code here. This is not impacting our compilation, which is going in parallel. As long as I don't hit the upload button, we are safe. I'm using the same construct here as before, but now I'm doing something special. Let me close the window here. I'm using the CO2 server. So I'm going back to this COVID-19 folder where we have the sensors. We haven't used the calibration of the sensor yet, but we have built something really interesting. We built a server that lives on the ESP8266. And this server gives us many things. One is a visualization, a nice smiley, which turns yellow, green, red, depending on the threshold. But as well, it gives us a button, like a web browser page, where we have a button which is password protected. And if you know the password, you can press the button and start the calibration of the sensor. So you basically bring the thing outside. You use your mobile phone, connect it to the sensor, go on the web page of the sensor and look for the button to calibrate it, and you're done. So you even don't need a button or any hardware to trigger this calibration. You use just a web page. How you do that is simple. You go for a Wi-Fi connection. If you want to connect it to your existing Wi-Fi network, then you would just put that into the setup. Or you're going to use an access point function where you can say your CO2 traffic monitor is called CO2 traffic. And so that's the SSID of that Wi-Fi hotspot. And the password is whatever you want to call it. And now later you can watch for this traffic, CO2 traffic access point. You enter this password and your mobile phone, tablet, laptop is connected to the web page of our sensor. We give the sensor a name, whatever it is, could be a classroom name. We need to put in a value for the CO2 monitoring. That's our variable that we have up here. We just copy it in here. You define first threshold and the second threshold, a sampling time. You can add humidity and temperature, or you do want to have in a curve. And then you pick the calibration button block here and just put it in the function called calibration. And you can specify the altitude of your location. So if you're at 800 meters above sea, just enter that, and the calibration will take care about that. And you need to specify, of course, a password for the calibration. And we need to have a delay somewhere. How often we want to sample this, like every 10 seconds or so. And you have a super cool traffic light that shows you even a web page and that you can share with the community.
Is it logging on the web page? Is it keeping the data?
Oh yeah, that's a good question. So if you see this web page spin up, and maybe we have time, maybe we need to cut it and show it depending how quickly the compilation here is going. But if you open this web page, you see the graph, and on top of the graph, you have an export function. So you can download actually the measurement to an Excel file. Actually, It's a CSV file, so you can use it with whatever tool you want. And so we are storing like, I don't know, 1,000 or 2,000 data points in there.
Okay.
But you can change that depending on the memory situation. How long is your program? And we need to keep it in the ESP memory. And therefore, we have, of course, some limitations. But now you could think about if you're good in coding or using the Arduino libraries, well, you can have an SD card reader here sitting and record it on an SD card. Or you use the Wi-Fi connection and use one of our other Superblocks to go to one of your favorite online platforms like ThinkSpeak, or even you can send it to your own HTTP server, or you can go with an MQTT to the Grafana dashboard that you have seen. So you have plenty of opportunities where you want to send the data, where you want to store the data. And even that works in an offline environment where you don't have any connections, as we show here. You're spinning off your own access point. Imagine your school doesn't have a public network. You're not allowed to connect that network, and you don't want to use a mobile network connection for that. Just make your own hotspot and connect your mobile device locally to the sensor. No charges, no security questions, how we connect things. It's all there, and control your hands.
Okay, how are we doing on the uploading the code?
Oh, we have uploaded the code. That's good. So I'm showing you how that worked. So you see the compilation went well. It connected to the ESP, it found it, and it transmitted the code to the Octopus or to the do-it-yourself version. Now I'm going to switch back to the table camera. I think I'm on the table camera. Yeah.
Yep.
And now you see the little code that we created, and let's test it. So we have the yellow light on. And if I haven't reversed the pins of the red and the green light, we should see now a red light going on when I breathe onto the sensor, right?
Bit of delay.
It's always a bit delay. Oh, wow, it works. Now we have a red light. So you see the CO2 molecules need a little time to travel into this sensor, even by breathing close to it. And that's what you have probably seen in the presentation earlier. It takes roughly 2 minutes that we get the aerosol spread equally in the room. And that's the same for the CO2. The CO2 molecules want to stay not together. They want to stay away from it. And so they distribute equally in the room. And now you see it's switching back to yellow. I'm opening the window here again and see maybe we see a green as well. So we have a fully tested traffic light system up and running.
Obviously, we'd like to see students building this for each classroom. They could monitor it and see it. Part of it is to use it to change behavior. And so you might, by say doing a week in one classroom, recognize the patterns that are generating the red light and even take the device away you still have those patterns. You can say, we don't have the windows open long enough. So you could theoretically build a single device and move it from classroom to classroom over a period of time to get different readings. It's actually the key thing that I think you did with the traffic light is it's one thing to log data, it's one thing to accumulate it. But if you're just looking historically at that data and say, it's spiking at 11 o'clock, that really doesn't help you change the behavior in the moment. The simple 3 LED pattern or the smiley faces are things that, especially when they're publicly or visible, can get everyone into changing that behavior. A kid in the back row might see it before the teacher does and raise their hand and say, let's open the door a little bit more. So that's what I think is exciting here is how physical the device is. It has to measure something that's invisible, but it is giving us a way to change behavior patterns in a group.
Absolutely. And I think another element that comes with it is this pandemic is, you can't see it, you can't smell it, you can't feel it, right? It's somewhere and we don't know really, is it in the room? Yes or no? Should we wear a mask? And if we are not seeing it, we typically as humans say there's no risk, right? If we see the tiger jumping and coming to us, we fear there's a problem arising. But if we can't see it, we can't smell it, we can't sense it, we think there's no problem maybe. Or maybe why should we wear a mask? Now, with this, we're showing there is something in the air. There's something happening. Even we can't measure the virus itself, but we are visualizing there is something. And
it's a dynamic system.
Yes.
Not a static one. It changes. Yeah. And I think the actual interest here isn't that it trips a certain level like 1,000. It's that it's moving up over 1,000 and it's moving down below 1,000. And
actually you can make a challenge out of that.
Right.
Who is ventilating best? Now you can take in consideration also CO2 emission for heating systems. So if you have the window too long open, you're wasting energy. If you're finding the right balance between keeping below that 1,000 threshold, not open too off the window and disrupting the teacher doing the study and so on, we now can find what is the best algorithm. And to spark on some creativity, what we heard is, well, beside the red, green, yellow light, we could have a counter telling us we have 50 minutes left till we need to open the window. So think about other algorithms and other ideas, how you can advance this. And maybe
Right.
you can make a challenge out of that at
Right.
your school and say, what are the ideas? How can we
Right.
use it?
Exactly.
Or you can take this thing to your dad's restaurants or mom's bakery or whatever and help opening their stores while you control the air condition there and you show it to the public and say,
Right.
he is safe to be because we take care about the air conditions.
Maybe the concluding point I'd like to make is just for teachers and students, particularly out there, is that in learning to do this, you're absolutely learning a real world application that's involving hardware and sensing, software, making decisions based on what the data is showing. You know, the display, again, how do we communicate this to other people? And then the analysis of or data visualization, all these things integrated in kind of a simple device here, but it's very powerful. And I actually think, as you showed in that one graphic panel that you had in here, I think there's a future in this of having smart room sensors that are independent from the heating system, independent from vendors. But you mentioned humidity, you mentioned temperature. How do these things correlate? What is comfort in this room to people? But we're also looking at what is dangerous, what is something that we ought to be warned about. CO2 is not just about the coronavirus here. Rising CO2 levels can impair cognitive ability. It can, someone I talked to said, yeah, you ever been in a conference room after lunch with the doors closed and everybody gets sleepy? It's because the CO2 levels rising in the room. Yes. Why don't we have sensors saying that? Why do, it's from a behavioral point of view, it's interesting to me that we as humans actually don't detect this consciously. We have to absolutely observe our own behavior to see that we're falling asleep, to think about what's causing that. We just tend to fall asleep and say, oh, we were tired.
And the same with the VOCs. So if you're looking at the VOC, you're wiping with a chemical or with a sanitizer at the desk, we smell it for a couple minutes, but then we are adapting to ignore that because we might want to smell something other important thing, because so we are adapting to what we are.
Yeah.
And then we are forgetting about that there's chemicals in the air, but the sensor is telling us still there's chemicals in the air.
Yeah.
It's not going away. These sensors are not adapting. They're still showing what's going on. And so we can always learn from other indicators. How can we advance what we are doing? How we can change our behavior? And I think the most interesting one, we can spark off curiosity in the pupils' minds and keep them curious about discovering their environment and find new ideas and solutions for other problems beyond what we are doing today.
You've been listening and watching MakeCast here, brought to you by Make Magazine, and I've been talking to Guido Berger from Germany, a creator of the Octopus board. We're going to extend this over time to encourage more people, particularly students, to build CO2 sensor devices, but it's not limited to schools, offices, bars, restaurants, churches. Other places should have these devices, and they should be visible so that not just one person in charge of the air conditioning knows what the problem is, but every person is aware of it and they can change their behavior accordingly. So thank you again. Thank you, Guido, for being on this. And I appreciate your wonderful explanation and demonstration of the CO2 device.
Dale, thanks for having me on today.